Okay, so we continue from where we ended. Okay, let's move on from there. Let's move on. We've already done the maximum, right? Now we proceed with now the last part, which is the range. Okay, we can call it horizontal displacement. Okay, that's the horizontal displacement. Okay, so let me cast it here. Range. Okay, that is the horizontal displacement. Okay, so with the range we are looking at this distance from there, okay, all the way to there. That is the range. Okay, which is the horizontal displacement. So what's the distance on the ground from point A to point C? Now, if you look at the range, you will remember from just basic or elementary physics that distance, okay, I'm going to call it range or distance, is equivalent to speed or velocity, if you like, velocity times time. Okay, so if you look at, in our case, the range, the velocity here is constant in the x-axis, and we say the velocity in the x-axis is u cos theta. Remember that. So we are looking at the range, which is in the x-axis, the distance along the x-axis. We've already looked at the distance along the y-axis, which is the maximum height. Now we are looking at the distance along the x-axis, which is it's called the range. So this range now is this distance from point A to point C, and the velocity there, as measured along the x-axis, we say that Vx is constant, and that Vx is equal to u cos theta. So we substitute it there. So substitute it here. So substitute this value there. So you have u cos theta multiplied by the time. Now, which time are we going to use? Okay, what time are we going to use? I want to see some hands there. Yeah, okay, I see you there. All right, so the time to cover this distance is actually the time of flight. Okay, so it's the same time from point A to point C. It's the same time that is going to be covered. It's the same amount of time that we're going to use as the time of flight from point A to point C. So in this case, we have the time of flight. Remember, we already derived the time of flight as time of flight, which we can call TF, is equal to 2u sine theta over g. Remember this, okay? This is what we took as, we derived as a time of flight. So u cos theta multiplied by the time of flight, which is 2u sine theta over g. So I'm going to erase this time of flight because we already dealt with it in the previous section. Okay, so in this case, you're going to have the range, which is the horizontal displacement, being equal to this u cos theta multiplied by 2u sine theta over g. All right, so we multiply this together, and then we are going to arrive at that value. All right, so if I multiply this and that, this u and this u will square. Okay, so I'll have this 2, which is this one. This u multiplied by this u would be u squared. This and this will simply be cos cos theta and sin theta, and this over g. If I give this a denominator of 1, so 1 multiplied by g, I will have g. This is the range. You can use this equation, but you can also use this other equation. This other equation is that, according to the identities in trigonometry, sine 2 theta is equal to 2 cos theta sine theta. Alright? So you can see from there that the 2 is there, which is this 2. We can see that the cosine is there, which is this one. We can also see that the sine is there, which is this one. So these 2 cos theta sine theta can be substituted with sine 2 theta. So this equation now, the range, will become u squared sine 2 theta over g. Alright? So if you're not clear, again, leave a comment, leave a question in the comment section, and I'll be able to respond. Let's do a recap together, okay? Let's go through a recap and look at what we've just discussed. Let's look at a recap of what we've discussed. Okay. First and foremost, we said we are looking at studying motion in terms of projectile motion for an object that is projected from the ground going up. There are so many different case scenarios that we're going to look at, and much of the questions will be given to you in the tutorials because there are different types of questions associating with projectile motion. You can have a trajectory, you can have an object coming from maybe a height and it's coming all the way down. Okay, you can have an object going all the way up, okay, and so on. You can have an object from a particular height, okay, from a particular height goes up and it comes down. So all these are different kinds of scenarios, but the equations still hold. Okay, so we started by discussing what projectile motion is. We say anything that is projected qualifies to be in projectile motion. But then, for this one, we've confined it to a two-dimension motion. Okay, we confine it to a two-dimension motion. With a two-dimension motion, we are saying that in this two-dimension motion, we have to look at motion. We have to study motion on the x or y plane. As you study motion on the x or y plane, you are saying, I want to know the behavior of this motion along the y-axis. I want to know the behavior of this motion along the x-axis at the same time. So for me, I'm interested to know motion. How is it affected along the y-axis? And at the same time, how is it affected along the x-axis? Because you're looking at two axes, hence the two-dimension. Alright. Then we say that looking at the projection of any object in the air, there are certain parameters that we can look at. And in this case, for projectile motion, we look at three parameters. That is time of flight, okay, and also maximum height, very important, maximum height, and lastly range. Of course, there are so many parameters at an advanced level that you can look at, aerodynamic parameters that you can look at, but for now we'll confine ourselves to these three parameters and say that an object that is projected at an angle, okay, an object that is projected at an angle on the x and y axis, you will have an object projected like that, and it was mentioned that this is initial velocity at an angle of theta. The initial velocity is called the velocity of projection, velocity of projection, and then there's an angle of projection, because this is the velocity with which the object possesses at the inception of its journey. All right. Then we said, because we are looking at motion in y and x-axis, this is the y-axis, by the way, and this is the x-axis. Because we are looking at motion in 2 dimensions, in this case, what we need to do now is to look at it dealing with a common figure, or common figures, or common parameters, velocity and the angle there. These would connect the 2 axes in the study of motion of this object. When we do that, what we are going to have is that if I resolve this one as earlier mentioned, if I resolve this one, we learn this under vectors. I'm sure most of you still remember, and I hope so. Okay, so you're going to have u sine theta there because you're stretching, and u cos theta because you're compressing the angle. Okay, so naturally the journey of this object will go that way. That will be the journey of this object. Okay, naturally that will be the journey. Now, within this journey, I mentioned earlier that it will have 2 sets of velocities, which we can call the Vx and the Vy. So there are certain parameters that you will need to know as you understand projectile motion. Is that number 1, keep it to your mind that Vx is constant. Keep it to your mind because it will really help you understand some of the derivatives that I'm going to repeat, having done that. Vy equals velocity in the, that is, I'm going to just call it velocity in the y-axis. Okay, that is to mean that this value changes due to gravity. Changes due to gravity. And because it changes due to gravity, it affects the velocity at that point. All right? Now, that's one thing we need to know, that velocity in the x is constant, and in the y changes, but except at maximum height, at the tip of the journey, at the apex. All right? At the apex of the journey, at this point, the apex of the journey, the object is no longer going up, so Vx still remains constant, but Vy is 0. Those are not certain things that you need to take note of, very important. And then also, when we talk about the range, we are talking about x-axis displacement. Okay, displacement in the x-axis. And also, this is displacement, which is the maximum height, displacement in the y-axis. Okay, we can call this one maximum height. Okay. All right, so we proceed. All right, so before I delete that, remember the time of flight is the time that it takes to go all the way up and coming all the way down. That will be the maximum height. I mean the time of flight. The maximum height is this one here. And the range is this one there. So the time of flight, maximum height, and range are 3 parameters that we need to understand. Okay, we need to know how to arrive at those. So coming to the time of flight, I mentioned that first and foremost, you look at the three equations of motion. The three equations of motion are that in terms of projectile motion, I'll not go all the way back, but in terms of projectile motion, we say the three equations are Vy is equal to u minus gt, this is u sine theta minus gt. Remember, everything else is Vy, Vy, Vy. The reason is that Vx is what? Thank you. It's constant. Alright? It's constant. Alright. Then Vx is constant, as we know it, but we'll not write it here. We'll have S being equal to U sine theta T minus half. This is half GT squared. Then you have V squared minus U squared and minus 2GS. But this, remember, has to be U sine, and that has to be squared. Okay. Okay, that has to be squared. So out of the first equation for the time of flight, we can make T the subject of formula, then multiply it by 2. Okay. So we have, in this case, Vy minus u sine theta minus gt. Change the subject to t, okay, which is time. In the brackets, I'll put time, which is half just the journey. So when I do that, I'll take this to the other side. I'll have gt equals u sine theta minus Vy, then we divide there, then we have t equals u sine theta. This is 0 because it's at maximum height, minus, we will just ignore it, divide by g there. Okay, so in that case, multiplying by 2 to get total time. Okay, so this becomes t equals 2 u sine theta over g. That is the time of flight. We've looked at that already, but I thought I should just recap and go through that for the sake of clarity. Okay, so this is where we're coming from. V equal to u sine theta gt, S equal to u sine theta t minus half gt squared. Then you have v squared equals u sine squared minus 2gs. And then what we did was to look at this first equation because it has enough parameters to calculate the time of flight, and made t the subject of the formula, going all the way down. But what we're solving for was at maximum height. At maximum height, which is half the time of flight. So at maximum height, it's the same as saying TF, which is the time of flight, divide by 2. But if you multiply by 2, you will get TF, which is the time of flight, all the way to the end. So in this case, we made Vy equal to 0 because they're looking at maximum height. The object is no longer going further up. Okay, so that becomes 0, and then you have 2u sine theta over g. Okay. Now, having done that, let's look at maximum height. Please record this, okay, in your notebooks. Record this in your notebook. It's very, very important to know those equations with regards to this particular study. Okay. Don't hesitate, okay? Don't hesitate to ask questions. It's very, very important. And make sure that every one of you is clear. Secondly, we look at the maximum height. The maximum height, again, at maximum height, we take advantage of the fact that Vy is 0. Okay, so we look at the last equation of motion. We don't want to use the second one because of what I mentioned it in the earlier post. Why are we not using the second equation of motion, for example? Okay, the reason is very simple. We have time in the second equation, and that's the calculated value. You don't want to get a calculated value and insert it in another calculation. What if you get it wrong the first time? What if you get wrong the time? Then you're trying to calculate another parameter using a wrong calculated time. So that's the reason why I'm not using it. So you have v squared equals u squared sine theta squared minus 2g. I change this to h max. I'm looking at that, the maximum height. So we're going to make this a subject formula. What is this is 0? So we're going to have 0 equals u squared sine squared theta minus 2g h max. Alright, so we take this to the other side. We have 2g h max equals u squared sine squared theta. I divide this 2g, I divide this 2g, that and that goes. We have h max being equal to u squared sine squared theta over 2g. So that will be the maximum height. Okay, I'll be giving you examples shortly. I'll give you 2 examples and then we can have a look at that. Okay, you can have a look at those 2 examples. All right. Okay. I will not complete those examples all the way to the end because I want you to do that with me. Okay. The last one is the horizontal displacement, which is the range. Remember, we say the range because it's displacement, so we're going to have velocity multiplied by time. From the basic physics that says distance is equal to speed times time. Okay, if you remember this, then it will be easier to remember that as well. It's one and the same. So we have our range being equal to the velocity in the x, because it's, remember we said it's horizontal displacement. In the x, we have u sine theta. And to cover this distance, you need the time of flight, which is 2u sine theta over g. So in that case, you have the range being equal to this and this will multiply. So you have 2u squared sine theta cos theta over g. Alright, so this constitutes the range of our journey, which is the x displacement, x-axis displacement. Now, let's look at an example. Let's look at an example. I'm going to delete everything, but if you have a question on this, leave a comment in the leave your question in the comment section. Okay. Let's look at the question, and I'm going to put the equations on the board for you to refer to them as we go. Okay. So I'll put them this side. So we have time tf, which is 2u sine theta over g. We also have maximum height, h max, which is u squared sine squared theta over 2g. Then we also have range, which is 2u squared sine theta cos theta over g. Okay, so this is time, this is height, and this is we'll say displacement. I'll put x at the bottom as a subscript x. Okay. All right. Having done that, let's look at an example. The example is that an object is projected 30 degrees, with initial velocity of let's say 4 meters per second. Okay. Calculate the following. Let's say the following. Then we list them. Okay. Calculate the following. Number 1, time of flight. Number 2, in that order, maximum height. And lastly, range. Okay. So already we have been given only 2 information. That is this one and that one. Like I said, I'm not going to finish this. I'll give you some time to wrap them up, but we'll go all the way. So if you look at the time of flight, in this case, okay, the time of flight is given by, in this case, we're going to say taking, it's very important to state this value, taking g equal to 10 meters per second squared. That's the acceleration due to gravity. The time tf is equal to 2, the initial velocity there is 4 multiplied by sine, the trigonometric function there, the angle that has been given is 30, divided by the acceleration due to gravity, we are saying it's 10. So the total time of flight will be equal to, sine 30 is 0.5, so this is half. So we have 2 multiplied by that, so we have 8 multiplied by 0.5 over 10. Okay, so this will give us 4 over 10, which is equivalent to 0.4 seconds. So that will be the time of flight. Okay. So in many cases, what I've seen students struggle with is how to use the sines, the cosine in the same equation. Remember, type everything on the calculator, administer everything on the calculator exactly the way you see them on your book. Okay, exactly the same. So that will give us 0.4 seconds, okay, as the time of flight. Record this because I'm going to delete it so that I keep the space. I want to keep the equations, I want to keep the question as well. Okay. Secondly is the maximum height. The maximum height, again, is the use of the calculator here. And make sure that your calculator is in degrees and not radian. Alright. So here we have the initial velocity 4 squared multiplied by sine 30. I'd like to keep the square outside. Alright. Divide by 2 multiplied by g, we said it's 10. So in that case, we have h maximum is equal to, this is 16, again, so 0.5, we have 0.5 squared. 0.5 squared is like 0.045. Okay, it's like, it's actually a quarter. Okay, so this is 20. So in that case, the system has 16, right? It's same as saying h max is equal to 16 multiplied by 1 over 4, okay, divided by 20, which this is 4 times. So we end up having 4 over 20. So the h max will be equal to 20 into 4 is 0.2 meters. Okay, don't say it can't. Okay, there's a decimal value there. Don't say it can't. Alright, that's the maximum height. Let's wrap it up with the range. sine 30 multiplied by cos 30, there's a dot there, means multiplication, divide by 10. So this range will give us 2 multiplied by, this is 16, or let's just say 32, or let's just say 3.2 sine 30 cos 30. Okay, this should give us the range in meters. The reason why I got this 3.2 is this is 16. Okay, 4 to the power 3 is 16. 16 multiplied by 2 is 32. 32 divided by 10 is 3.2. Okay, and then type everything on the calculator and leave the answer in the comment section. All right, leave your answer in the comment section. Let me see your answers that you're going to get. Okay, and your friends will be able to see that. All right, so there's no wrong or right answer. There's just the correct one. Okay. Okay. So that leaves us with so many things that we can now look at in terms of projectile motion. Much of what we discuss here is a summary of what is in your notes. So attached to this video